So, welcome back everyone to the day 4 or the part 4 of the CUDA programming series. And in this video, we'll be looking at something called atomic addition, reduction using some sort of a binary method, as well as warp shuffle ideas, and just getting a basic understanding of all of this stuff. Now, before moving on, what is a warp? So, we already know the thread hierarchy or a block hierarchy or a memory hierarchy. When we invoke some sort of a CUDA kernel, we launch a grid. Each grid has multiple blocks. Each block has a thread. And each of these thread are part of some sort of a group called a warp. Although they are part of the block, thread block also, but they are a part of a fixed group of 32 threads per warp. This number is fixed in the GPUs. It is always 32. You cannot set it as far as I remember. Now, the property of a warp is that each thread, so suppose T1 to T32 are the threads in a particular warp A, then all of these threads in a particular warp can access their values in each other's registers without calling sync thread or using the shared memory as well. So recalling, we have a global memory, we have a shared memory which is common to block, and all of the threads within this block, you can have T1 to Tn within a particular block, they can do a very fast access of any element from the shared memory. But within a warp, there is something called uh, a warp memory or register backed memory where these threads can access data from each other threads very easily without the use of sync threads. You will remember that we use sync threads to update the shared memory as well. Now, I hope this is clear. Pretty simple. Each thread is a part of 32 thread group called warp. They can very easily access each other's memory and try to read from it, and it is extremely fast compared to reading from shared memory also. So suppose this is the chip. We will have, let's say, registers, then cache or shared memory. Then at the end, we will have the global memory. The global memory has the largest in terms of memory bandwidth, but slowest in terms of the speed. Whereas registers are lowest in terms of memory, but the fastest in terms of speed, right? So this you need to remember. So we need to make sure that we can utilize these registers very well. Now moving on to what is a reduction. A reduction is a very simple operation that you can do which reduces some sort of array or data into a very smaller piece. For example, sum of, let's say, array is defined as of all elements of array I going from 1 to n. This is a reduction. We are storing the sum of all these elements in an array into a variable called sum. Another operation can be called minimum of a is minimum of all elements I going from 1 to n, right? This is a reduction algorithm. Same goes for subtraction or multiplication or everything like that. So on CPU, if you are writing a sequential algorithm, how will you calculate this thing, total sum of an array? It is simple. You will declare a variable called sum equals to 0, loop from, let's say, 1 to n, and do sum plus equals to array of I, right? But if n is very large, let's say around a million elements, and since this is sequential, this can take a very large amount of time. You also need to remember that a CPU has very low number of threads available, whereas GPU, it focuses on a very large throughput a little bit of latency trade-off compared to CPU, but it tries to manage that by invoking thousands of threads, millions of threads, right? And when we invoke a kernel, each of these millions of threads will run this kernel, a particular kernel that we define. So there is some sort of opportunity to parallelize this, right? How will you do that? Let's say we need to write a kernel that takes an array A, some sort of output variable out, and does this. Sum of all elements of array is stored in the variable called out. Now, what we can do is, let's take an example of n equals to 4. There are 4 elements in an array. We invoke 4 threads, T0, T1, T2, T4. So there will be 4 kernel calls. And since these are only 4 threads in a block, we only require one block size for this problem. Threads per block is 4. The size is very less, and 4 is much less than 32. All of these threads will be lying in the same warp, hopefully. And all of these kernel calls K1, K2 of associated with each thread will be happening simultaneously, right? In that case, this kernel can read A0, do this. This kernel can read A1 and do this. The third kernel, same way, can do this sort of thing. Fourth kernel can add A3. In this case, we can do it. But the problem, very famous problem with concurrent or parallelism, although both of these things are different terms, but using them together, a very major problem that arises from this situation is called race conditions. So race condition basically happens when a particular thread, let's say T1, tries to change or read from a memory location M, which is also getting read by T2, and T2 has not finished updating this yet. So let's say out is currently 10. T1 accesses the data. It is doing some operation. And while it is trying to update this by, let's say, 1, the job of T1 is to update out by 1. Before that happens, T2 reads it. The thread 2 reads it. Now thread 2 has out as 10 instead of 11. So this will always result in wrong outputs. So this is in short something called a race condition, and how you solve it is, in especially in CUDA or in anywhere. I guess in CPU parallelism or concurrency we call in C++ I guess it is called atomics. There is a header called atomics if I remember correctly, or thread.h or threads. But moving on to the GPU part of it, especially in CUDA, we use something called atomic operations. And in our case, where we need to get the addition of the entire array stored in a particular variable, we do atomic add. Now, what atomic add does is it takes care of this race condition and makes sure that each thread has the updated value of a particular variable that they are trying to access. So the function signature is simply like this. You have your output variable here and the value you want to add it, x. So after this, out will have this thing. We are adding x in it. But just using atomic add takes care of all these problems of race condition, parallelism, or threads not updating, or everything like that. Remember, in this case, you cannot use something called sync thread. You need to use atomic addition when we are trying to do reduction problems. This is something that you need to remember right now. But just using sync threads won't work. When we do a very high level optimization of particular kernel, we try to use these together, and we will see how it works. Now, going to the code of how to write a simple atomic operation, it is very easy. So this is how your kernel will look like. You will have uh, the DA, which is your device array, and an output variable where you will store the result of the sum. You'll find out the global index of the thread that you are working on. Do a bound check, call atomic add, and the value of array A at the index IDX will get stored in, or added in D out. And rest of the code is almost always similar to all other kernels. We are just allocating memory and copying from host and device and everything. I have already uploaded it on GitHub. You are free to look. I will be pasting the link in the comments. But the basic kernel is this. This is a naive kernel. So this will work as our baseline on anything that we are trying to improve over this. Moving on. Now let's say there is something called binary reduction while we are doing um, addition operation in threads. Let's say you have an array with elements 1, 2, 3, 4, 5, 6, 7, 8. And you define threads per block as, let's say, 4, and each thread will handle 2 elements. We will see how we will be doing it, but for now, each thread will handle 2 elements, right? So 4 threads will handle 8 elements, and it will cover the entire array. So the number of blocks that we will require is 1 block, and the block ID in that case would be equals to 0. Now let's look at it. How do we do this operation of each thread handling 2 elements in a particular array? So we do it like this. We define int idx as a block dimension dot x multiplied by block id dot x plus thread id dot x, right? Let's start with the first one. So block id in every case is 0, so it will go to 0, and the idx will be same as thread id dot x in our case, which will vary from 0, 1, 2, 3. Yeah, because we have only invoked 4 threads. What will thread 0 look like? So thread 0 will handle 2 elements, 0, which is at index 0, and another which is at block dimension dot x. In our case, block dimension dot x is equals to 4. So another at index 4. So T0 will handle 4 elements, 0 and 4. T1 will handle 2 elements. Uh, did I say something different in the earlier sentence? So thread 0 will handle 0 and 4th element, which are this and this. First thread will handle first and fifth element. Second thread will handle second and sixth element. Same goes for the third thread, fourth thread, T3, which is 3 comma 7, which are this one and this one. Now, what we can do is the job of each thread can be to calculate the sum of those two elements, let's say E1 and E2, and store it in some sort of for shared memory. So there are 4 threads in a particular block. We will define the shared memory size as 4 itself. So it will be made up of 4 elements. Now T0 will compute A1 plus, sorry, A0 plus A4, which in our case is how much? Let me zoom it out a bit. A0 and A4 is 6. T1 will be computing A1 plus A5, which equals 2 plus 6, 8. T2 will compute A2 plus A6, which will equal to 3 plus 7, 10. Then finally T3 will compute A2, sorry, A3 plus A7, which will equal to 12. Now the shared memory will have something called 6, 8, 10, and 12. Now, these threads will, now we will apply something called binary reduction over it. So let's say we combine these two elements again. We will get 18, 18, combining these two again, we get 36. So the sum of these elements should be 36. And we are getting that same thing here again. So let me revise it. So your elements are 1, 2, 3, 4, 5, 6, 7, 8. Let's say you sum these two together, or let's say you sum 1 and 5, you get 6. You sum 2 and 6, you get 8. Similarly, you get 10 and 12. This is first step. In the second step, let's say you sum these two together, you get 12. You sum these two together, you get, sorry, you get 16 and 20. And in the third step, you get 36, which is the final sum of it. So instead of doing ON operations sequentially, doing addition sequentially, we did it in login terms or login steps. So log 2 of 8 is 3. You can see we did 3 steps, and the final one would be the sum of the entire array. So there is an opportunity to implement this particular algorithm in our case. So let's understand how the code does it. Let me open that file that I was working on earlier today. Okay, now we will try to understand what each line of this particular kernel means very, very elegantly, I must say. It also took me a long time to understand how everything is working. Now, the first thing that you will need to understand that we are declaring a shared memory of size threads per block. So all of the threads that are in a particular block will have access to this particular shared memory, and we have defined the size of threads per block as 256. Now we are calculating block dimension dot block index times 2 plus thread index. Have I mentioned it earlier or not, this formula? Okay, I should have told you this is not correct. We need to multiply it by 2. Now how it works is, let's see. So as we saw earlier, we had 8 elements, and just because each thread will be handling 2 elements, we need to invoke almost half of number of the blocks. So the block 0 will have, let's say threads per block is 4. It will handle elements. T0 will handle elements A0 and A4. T1 will handle A1 and A5. T2 will handle A2 plus A6. T3 will handle A3 plus A7. In our example of only 8 elements, this particular problem is solved. But suppose if we had 16, so instead of one single block, we will require 2 blocks in that case. So the first block, which is B0, will cover elements from all the way A0 to A7. Right? Now block 2 which is B1. ID is 1. The formula, remember the formula, which is block dimension dot x times block ID x dot x plus thread ID dot x. This will vary from 0 to 3 again. Block dimension is 4. So 4 times 0 is what? Let's calculate the index. 4 times 1 plus 0, it's 5. Yeah. 4 times 1 plus 1 is 6. Then 4 times 1 plus 2 is 7. Then we have 8. So these will handle A5. See, I was a little bit confused. What am I doing wrong? I forgot to multiply by 2 here. So do not make this mistake. This would have been very awkward if I did not figure out the mistake. So this is what it is. 4 times 2 is 8. This is 9. This is 10. This is 11. So thread 0 in block 1 will handle elements A8 and A adding 4 A12. Thread 1 will handle A9 plus A13. Thread 2 will handle A10 plus A14, and thread 3 will handle A11 plus A15. So these two blocks and 4 blocks in each of those threads combined together covered all the 16 elements in our example. That's why we are multiplying by 2 here. We're just storing thread ID for later calculations purpose. Now to apply reduction formula correctly, the level 1 that we discussed here, we need to store something in the shared memory, right? So this step is doing that. It is checking if we are declaring something called sum, storing 0 in it. So this will store the sum of two elements that a particular thread is handling. So let's say in our case, we will store the sum of 0 and fourth element, first and fifth element, second and sixth element, third and seventh element, and so on. So we will have 4 sums in the shared memory. Then we are doing another bound check, that if I plus block dimension dot x, so I is the first element and I plus block dimension dot x is the second element that a particular thread will be handling. If it is less than n, then we are adding that particular element to sum as well. Then we are storing that sum in a shared memory and we are doing synchronization of all the threads. So before we do any further operation, we need to make sure that all the threads have completed this part at least. So this calculation of initial sum should be stored in the shared memory. Now we move on to something called the later layers or the steps of reduction. So you will see we are starting by with int s equals to block dimension dot x by 2 and so on. In our example of 8, this won't work, but if you have a large number of threads, this will work. So we are doing the same thing again in the first level. Let's see how it works very easily. We are starting with block dimension dot x by 2. So suppose you have defined threads per block as 256. So block dimension dot x will also be equal to 256. So the for loop will go all the way from 128 and it will stop at 32. So we will go in the steps of 128 to 64, and when we reach 32, it will stop. So in the first loop, as you will observe, we are checking if the thread ID is less than s. We are at 128, and if the thread ID is less than s, we are doing reduction. So let's start with stid plus or equals to whatever that is. So let me write it down, tid plus s. In our case, s equals to 128. So this will not work for the threads with the thread ID higher than 128, right? So let's say if the thread ID is 0, so we are just adding the value of on an offset of 128, and we repeat this particular step again and again till we hit 32. So when we are at 64, we will add 0th element to let's say 64th element, and then we are storing it again in the shared memory as well. Now, what happens when we reach at the level of a warp? When we are at the size of less than 32, when we have only 32 elements to sum, we can use something called the registers of a particular warp to not use sync threads. You will observe that for this particular operation, we are using sync threads, but when we are at the warp level, there is no need to use it. We can directly access the values stored in the other uh, threads of a particular warp. So, since we were at 32, we were just summing the entire value of the partial sum from the shared memory from STID to STID plus 32. Then we are starting to break it down in terms of levels and each time dividing it by 2. So we are starting with an offset of 16, and we are adding in the values something using the function called shuffle down sync. Shuffle down sync is enabling us to get the value of a particular thread at the offset. So suppose offset is 4 and current TID is 0. And we use this function called shuffle down sync. It will return the value of T4 to T0. If we are at T1, it will return the value of T5. If we are at T2, it will return the value of T6 and so on. And when then we store the final value in the shared memory. And as we saw in the example, if we do all of the reductions, then the final TID, when TID is equals to 0, it will have the total sum of the particular array stored in it. So when we reach the thread index 0, the atomic addition, we do an atomic addition to the output variable and store the result of the first element of the shared memory. Now this particular function signature of shuffle down sync is particularly strange. First thing is called a mask. So this particular mask tells the compiler that all of the particular threads in a particular warp. I say a lot of the word particular a lot of times. I'll stop saying it. So in that thread, in that warp, all of the threads are active. Consider all of these threads in the operation. We require the value val from there, and the offset is defined as offset, which is the part of the for loop. And then when we are finally ready, we will store the value in the shared memory at the index TID of a particular thread. When we reach TID equals to 0, which will contain the sum of all the elements, we just do an atomic add operation to D out as well. Why do we need to do atomic add? So uh, each block will have its own shared memory. So the first element of the shared memory of each block will contain the sum of all those elements that a block handles. So in our earlier example, first block was handling elements from 0 to 7, and the second one was handling from 8 to 15. So the first element of shared memory of block 0 contained the sum from 0 to 7, and same goes for block 2. Then we need to do atomic add of all those shared memories first element, right? And then store it in the final output. I have added this code in GitHub repo as well. This is a little bit confusing to understand how it works. So you have to visualize it using pen and paper. There is no other way. So just like I have done writing a very simple array of 1 to 8, you can do that too. Now let's look at the speeds. Please connect with the server collab. It did. So the first one, okay, first run this one. Let's run this one. So we are first running the naive one, which was the simplest one to run. The speed is around 3.8 milliseconds for around a million elements array. But the atomic reduction or the warp using the warp shuffle, we have around zero point 0.2 milliseconds of speed, which is around what? 20 times, 18 times faster than the naive one, which is a very huge number. And sum in both the cases is same. So this reduction concept is very fun to see. It is pretty easy to see when you are making a tree, like where is that tree one? Tree something like this. It is a little hard to see how it is working in when writing a kernel because it gets a lot confusing. Why are we updating shared memory like this? Why are we using some sort of an offset we are using because we need to divide these we need in each particular layer we half the shared memory or the sum that is taking place or effective size of the array, something like that. So it is very confusing at first, but once you play around with it, run the code on your own and change something, like make the change of not doing this particular step from line 32 to 34. Do this and see what happens. The result won't be the same, but you will understand why do we need to do this. Try to delete this particular block, check what happens. Try to understand why are we stopping at 32. What if we stop at 0, s greater than equal to 0? The code will work, it will be a little bit slower because we are not taking the advantage of the speed of registers that are allowed by a particular warp hierarchy and how they can share the data very fast between them. So try to remove this and change 32 to 0 and see the speed how it is working. Okay, thank you.